Welcome. We are going to be working ahead here on relativity things. The test today does not have a special calculus problem. You'll have exactly the same test as the 152 people because we didn't really cover anything. We did the one derivation, but because of our review time, we didn't really cover any calculus for optics, which is not a huge loss. Fraunhofer and Fresnel interference would have been good for us to cover, but we didn't. So won't be tested on that.
So we just get the same problem as still.
Yes, that's right.
Wow. Which would probably be one of the ray tracing ones.
Well, you're going to have a ray tracing problem. I mean, yeah, how do I say which one's which? Because you just all have the same. You'll have a ray tracing problem. Then you have another problem on chapter 24, another problem on chapter 25. Or 25 and 26. Yes, thank you. Yeah,
You gotta get calculus out of my head now. I'm like, get away from calculus. It's not happening.
Okay, so what we're going to talk about today is Lorentz transformations. Y'all down with Lorentz? Yeah. Haven't met him yet. Okay. Well, let's get into this. So one of the things that is more of an advanced topic in relativity is dealing with events. Events are specified by not just the three coordinates of space, but also time. For instance, we have our Physics 252 class at 11:30 a.m. Tuesdays in this classroom. That's specifying a time and a location. And so it's not some crazy idea that we have to specify those. And the whole idea of relativity is comparing measurements in one reference frame to measurements in another reference frame. And we've already identified that they're going to be correct in both reference frames, even though they're different. So there's not a correct and an incorrect. There's just different measurements. And we've learned about length, well, time dilation first. That is, when something is moving, the rate at which time passes in the moving reference frame compared to one that we're going to consider stationary is different. And so we have that time dilation equation that said that the time measured in one reference frame is equal to the time measured in another reference frame divided by square root of 1 minus beta squared, where beta is defined as V over C. But we also defined a new thing here, gamma equal to delta T0. It has a name. It's the Lorentz factor. So already you can see, hey, Lorentz, now we're getting to introduce him. That factor is the one named after him. What did delta T subscript 0 stand for?
Time initial.
Not time initial here. It would have in the past. So it's a good answer, generally speaking. But not in relativity. Yeah, T subscript 0.
Must be the change of something.
It's the change in time, but it's
Relative to that.
Yeah.
it's a word that we often confuse with meaning correct.
Oh, it's the. We did it with that one.
The proper time. One of the keys with our relativity, like for the next test, is being able to identify which reference frame is going to be measuring the proper time. The reference frame in which the clock is stationary and all events occurring at the clock is the one that measures the proper time, or occurring in the same place with respect to the clock. And then we have, based on that equation, thing that we worked out at the end of class Friday, we have a length contraction equation as well. that the length of something is different in a different reference frame. How do we work that out? Remember, we talked about the astronaut or whatever traveling from here to something 30 light years away. But we determined that he, at his speed, saw it as only 22 and a half light years away. And he's correct. Both are correct. And so the length was shorter for the moving one. And we called that, and we didn't get into the details of it, we called this the proper length. The x subscript 0 is the proper length. And then x is the contracted length. So we had dilated time, contracted length. So we're going to go with that. Those are our starting points here. And we have this thing that is called a 4-vector invariant. Now, invariant is not some complicated words. It means it doesn't vary. So a 4-vector invariant is going to be some kind of equation that isn't going to change when you move from one reference frame to another reference frame. So that's what we're looking for. And we're going to find one here by using a flash of light. So we have two reference frames, same picture, two reference frames, and we set the reference frames so they're synchronized so the origins overlap at time equals 0. So what we're saying is we have reference frame 1, reference frame 2, moving at constant speed with respect to each other, and at time equals 0, they're passing right past each other. So we say, okay, here it comes, here it comes, here it comes, and the time that they pass each other, they both punch their buttons to set 0 on their clocks. Understand that synchronization? Now, at the time they press that button to synchronize their clocks, we're making this up as we go, so we can make up whatever we want, and we're going to say that when they punch that button, a light flashes. Now, if a light flashes, what direction does the light travel?
Wherever it's pointing.
Okay, wherever it's pointing is a good answer. Let me be more specific. If it is a light bulb, a little light bulb,
No, it
travels in all directions. And how's the speed in this direction compared to the speed in that direction? Same. If we're in a vacuum, and since we're making this up, it's going to be in a vacuum, of course. We're in physics class. What else would it be in? So it's in a vacuum. The speed is the same in all directions. So that light is going to expand out as Trace indicated with his hands in a spherical shell. So what is the equation for the radius of that spherical shell? It's written. That's supposed to be an R. The radius is the speed of light multiplied by the time that has passed. Now we have two reference frames. This one we call reference frame S, and this one we call S prime. So we just use the prime to differentiate which reference frame is which. And so you see we have primed variables for everything in the S prime frame, except for I cut off the Y prime. You can see I cut off the top of the Y as well. Nice job. And so this is equal to R prime. So each one is expanding in a sphere as measured in its reference frame. And that sphere has radius R or R prime, depending on which reference frame you're in. How else can you determine the radius of a circle? If you're using the X, Y, and Z coordinates, how do you determine the radius of a circle? Well, for a circle, you'd only have X and Y, right? How do you determine the radius of a circle in terms of X and Y? 3 of you are in calculus. You've done this a lot recently.
Say the question again.
In terms of X and Y, what's the equation for the radius of a circle? Okay, so I'm going to do R squared just so I don't have to do square root. X squared plus Y squared. That was for a circle. We're doing a sphere, and all you do is you add that last dimension. So the radius for a circle in terms of X, Y, and Z is R squared equals X squared plus Y squared plus Z squared. So now what we're going to do is say, well, we have two equations now for radius. One radius is CT. So I'm going to put c squared t squared. The other one, x squared plus y squared plus z squared. Remember, I'm looking for an invariant, something that won't change from one reference frame to another. So if I take this and I say, well, r squared minus r squared is equal to, by definition, 0. But that would be equal to c squared t squared minus x squared minus y squared minus z squared. Since it's always equal to 0, it's an invariant. It doesn't matter what reference frame you are in. Ct squared plus minus x squared minus y squared minus z squared is going to be equal to 0. Doesn't seem like we've done anything useful yet, does it?
No.
But what we have done is we've defined something we can use to make our 4 vectors. So we're going to make 4 vectors. We're going to make a vector with 4 pieces. The first one is going to be CT. The second one, X. Actually, I'm going to make the column vector first because the column vector has plus signs. CT, X, Y, Z. So those are our coordinates for our 4 vector. Now notice it's C multiplied by time. Kind of important because that gives it the same units as the other ones. Instead of having a different unit for one direction, they all have the same units. And so when we talk about space-time continuum calculations, oftentimes we use CT instead of T. All it's doing is multiplying by a constant, but it gives you the same units. Now let me go to the next 2 slides, actually. Nope, 3 slides. I did all of the work in those slides. I just did it for you all in one slide. So here is what we're going to define for our radius vector. And if we want to find the magnitude of the vector, we would normally do r dot r. R vector dotted to r vector is r squared, right? Well, with this 4 vector, we have to change our rule just a little bit for how you do a dot product. Remember, dot products, what you've done so far, it's x component times x component plus y component times y component plus z component times z component. Well, here it's a little bit different. We take this vector, and when we change it from a column vector to a row vector, we change the signs of the spatial ones. So notice we have minus signs here, here, and here, changing the signs of the spatial ones when we changed it from a column to a row. This is part of what you actually have to do mathematically in relativistic physics, part of the math. And so when we do r squared equals r vector dot r vector is equal to how many people are comfortable multiplying a row vector by a column vector? Yes, Chad better raise his hand. He's had to do it. Nathan says he is. The others didn't raise your hand, so let me go through just how this works. When you're multiplying vectors or matrices, you take a row in the first one and a column in the second one, and you multiply the components in order, and that makes the result in the row and column that you used. So in this case, it's 1 row and 1 column. So I'm only going to get one result here because it's going to be row 1, column 1 is the only result. And then to do it, I'm going to take the first item in the row times the first item in the column times, or plus, the second item in the row times the second item in the column plus the third item in the row times the third item in the column plus fourth item in the row times the fourth item in the column. So go ahead, Trace.
So obviously I get, I can see the outcome of this, but is this not, like if you had an X and a CT, would it just be X, CT, they will multiply together? Or is it just like a dot product where you can only multiply the same things?
Well, it is a dot product.
Yeah.
Yes, it's a dot product, so you only can multiply these terms, right? This one here cannot affect anything except for this one.
Yeah, but like if you had an X in the first spot, if it was like X minus X,
Oh.
CT.
The way to read this, to put it into what you've done before. Okay, so have you used I, J, and K to indicate directions. So let's just put H in front of I. So it's like we have
Okay, so we just remove
CTH
it.
unit
Okay, no, that ain't
minus XI unit and so on.
So you have to apply like CT times CT on the column. So one.
Right, CT in the row times CT in the column.
And you do it for each variable.
And then you do it for each one. So in this one, it was pretty simple because it was the same thing in the row and column except for the minus sign.
So what if they were different?
So what if they were different? Actually, this wasn't. It wasn't the. Well, what if they were different? You would still use the same format. So if it was like, let's just do a general. I think this is what you're asking. Let us say, what if I have A, B, C, D, and I multiply that by B, D, C, A. Okay, so I use the same variables in both just because I didn't want to get myself too out of whack. So that would be the first times the first, so AB, plus the second times the second, plus the third times the third, plus the fourth times the fourth. Obviously, if I would have said E, F, G, H, then it would have been all uniques. Okay, so that's how we multiply these four vectors together. Have we gotten anything useful? No, but we're going to. We're going to because we're now going to apply what we've learned about time dilation and length contraction to how we can convert from what's measured in one reference frame to what's measured in another reference frame. That's useful. So we start with, because we've learned that there's a linear relationship between the proper time and the dilated time, and likewise a linear relationship between the proper length and the contracted length, then it stands to reason that we will say that the primed reference frame is equal to some linear combination of the position in the unprimed frame and the time in the unprimed frame, and likewise for position. And so what I have here is two proposed relationships, that the position in the prime frame is what? Okay, I have it in the wrong order from what I just said. The time in the prime frame is AT plus BX, and the position in the prime frame is CT plus DX. And what we want to find is what the A, B, C, and D are. Now, what's the difference in above the line and below the line?
One of them is matrices.
Okay, one of them is showing the equations separate and one of them showing them in matrix form, but they're exactly the same equations. Using the rules we just learned, if I take this and multiply through, I would have T prime, X prime, there's nothing to multiply there, equals, I'm sorry, that color probably doesn't stand out. Oh, it stands out better there than I thought it would. This will be harsh. So I take a row times a column, right? That's what I said. So I'll take row 1 times column 1, and that's going to be 1, 1. So row 1 times column 1 is going to be AT plus bx. Now I'll take row 2 times, again, there's only one column. So row 2, I changed the color. I did. There. Row 2 times column 1, and that's going to be ct plus dx. And then you just say, well, the thing that's in the top must be equal to the thing in the top. So we have t prime is equal to at plus bx. Right? They're the same set of equations written in different forms. Well, how do I find the values for a, b, c, and d? Here's how I do it. I start by saying, okay, here's my reference frames again. And I have some event here. And I measure the distance from the origin to that event in my prime frame, and I call that x prime. And I measure it in my unprimed frame, and I call that x. And so my goal is going to be, well, how can I find x in terms of x prime? And you have two pieces. If you just looked at the lines, if we weren't doing relativity, how would you relate x and x prime? Well, just look at the arrows. How would we relate this long x arrow with the shorter x prime arrow? It does look that way, but that would just be if you took it at exactly the right time. We go from here to here, and then from here to here. So we should have x is just the sum of those two, right? Vt is the distance that the prime frame has moved. Its origin is moved from the origin of the first frame when we synchronize, right? From that time on, Vt is how far it's moved. And then x prime is the distance measured in the prime frame. It's measured in the prime frame. The prime frame says the event was there. I measured a proper length. And so the unprimed frame says, oh, it's actually going to be contracted from what they said. And so in the unprimed frame, that distance x prime is x prime over gamma. And since we're making how big is it in the unprimed frame, we have to use the contracted length of this, not just x prime. That's where relativity comes in. If we didn't have to use the contracted, we would have nothing. I mean, we'd have nothing different from anything else we've done. So we have the position of this event measured in the unprimed reference frame is the distance that the origin has moved as measured in the unprimed frame times the contracted length measured in the primed frame. Contracted length in the primed frame so that we get it back into the unprimed frame. As I say primed frame and unprimed frame, it starts to get muddled in my head. I should have color coordinated these. So we have to take the contracted blue length to get what it's going to be in the magenta reference frame. So, of course, I had that equation right there. And then I'm going to solve that for x prime. Remember, I had here x prime as a function of t and x. So that's why I'm solving it for x prime. So to solve this for x prime, I have to subtract vt from both sides. So I have x prime over gamma is equal to x minus vt. And then I have to multiply both sides by gamma. So I have x prime is equal to gamma times x minus vt. So that's one of my two equations. I can say right away, hey, look, x prime equals ct plus dx. My c must be equal to minus V gamma, right? And D must be equal to X gamma. So I found C and D already. Huzzah. Yay. Go team. You guys are totally down with this and excited. Sadly, I remind myself of a teacher I had in college that we all laughed at. You know, he gets so excited when he does something right. Well, yeah. I mean, you should too. All right. Now we're going to reverse it. Now we're going to say, well, what if the person in the prime frame is measuring the position in the unprimed frame? The same principle holds true. It's just that the speed of the prime frame was considered positive, so the speed of the unprimed frame we're going to consider negative because they're equal opposite directions. So we have x prime equals minus vt prime plus x over gamma. So remember before we had x equals plus vt plus x prime over gamma. So we switched where the primes are because we're changing reference frames. And with changing reference frames, we had to put the minus sign here in front of the v. So now with this is solved for x prime. This was solved for x prime. So I'm going to set x prime equal to x prime. I don't know why. It showed it momentarily as I wrote it, and then it disappeared. So we just set x prime equals to x prime, and now we're going to solve it for t prime. Because we want to get an equation that has the form t prime is equal to at plus bx. So solving this, so I'm going to do my own work down here. I have gamma times x minus vt equals minus vt prime plus x over gamma. Well, clearly the first thing to do is going to be to subtract x over gamma from both sides. And so that's going to give me minus vt prime equals gamma x minus x over gamma minus vt gamma. I almost forgot one of the gammas there. And you look at that and you're like, well, that's a start. Let's go ahead and divide everything by minus v. So I have t prime is equal to, and I'm going to factor out a gamma. Gamma over v. Change the signs of everything. So these things that were negative or plus, the thing that was plus is negative. Factor an x out of those first two terms. So this x was multiplied by gamma. I factored out a gamma, so it's just going to have a 1. Except for that's a minus 1. Let me put that minus 1 over here then because it's negative. This one here had x over gamma. If I factor out a gamma from 1 over gamma, what do I get? If I factor out a gamma, that means I'm dividing by gamma inside. So 1 over gamma divided by gamma is 1 over gamma squared. And then we have plus VT. Notice I factored out the V, so that's why it still has a VT there. Let's do some quick math. So there I substituted for gamma. But 1 over 1 over, what does it mean if I have 1 over 1 over x? Just x. So that square root thing is going to be on top. And we're squaring it. So we're getting rid of the square root. So that first term is simply 1 minus v squared over c squared. And then we have the last term, minus 1. Well, the 1 subtract out. And so this thing that's in parentheses here is just equal to minus v squared over c squared. That means this is equal to gamma. And now I'm going to bring the v in. Now I have it in the form I want. So coming up here, of course, this is the same thing except for I reverse the order. I put the positive first, so I have the t minus. And so now I can read once again, that's a t plus bx. So a is equal to gamma, and b is equal to minus gamma v over c squared. So now we found the 4 terms for my linear transformation. So I have put it in my matrix form down below the line or in the separate equations up above the line. One thing I should point out that I haven't said at all yet, length contraction only applies in the direction parallel to motion. Now, time dilation, there is no direction for time, so there's no such thing for only in one. But length contraction is only in the direction parallel for motion. So, certainly at this level in physics, we always assign, okay, I don't care what my dimensions are, whatever dimension reference frame B is moving with respect to reference frame A, that's the x direction. And thus we can make a 4-dimensional conversion matrix that just has ones for the traces of the next. So we can put t prime, x prime, y prime, z prime equals gamma times 1. I didn't give myself enough room. Well, I will shift it now while I'm thinking about it instead of waiting to the end. Minus v 1 0 0 0 0 1 0 0 0 0 1 t x y z. That's a perfectly good transformation matrix. But this is not, I'm sorry, it's not the 4-vector. Okay, yeah, I think I'm good. This is not the 4-vector that we had defined. What was the 4-vector we had defined? That. What's different? I will highlight what's different.
Yeah.
What we just did didn't have the C. So what I'm going to do is I'm going to quickly say, how would these equations change if I put the C there? So if I put a C there, it's going to change it like that. And so that means this is going to be, if I make it TC, I'm going to have a C on top, which cancels that C. And then down here, this over C is the same as multiplying this side by C. And then I'm going to have that C comes in here and it's CT, comes in here and cancels one of those. And so now I'm going to have this 1 remains a 1. And this V becomes a V over C. Did I do that right? Yeah, I did. I did, except for I put the wrong one first. This one here was the one that went to there. This one here is the one that went to there. And so we could also write this as CT prime, X prime, Y prime, Z prime equals gamma 1 minus, and let's make life easy, minus beta 0, 0, minus beta 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, CT, X, Y, Z. So here we have a transformation matrix for transforming a vector in one reference frame to a vector in another reference frame. How we usually use this, especially in class at this level, is we say this translates out into these equations where I defined x0 is CT, x1 is x, x2 is y, x3 is z. So here's the transformations to get my x0 prime, y0 prime, z, or x0 prime, x1 prime, x2 prime. And here's the reverse transformations. What's the difference in the reverse? These signs. So these are what are called the Lorentz transformations. This is how we can transform from one reference frame to another. So if I have an event that occurs at 11:30 a.m. at position XYZ, I can use these calculations to determine what time did it occur in another reference frame. What was its x coordinate in that reference frame? And like I said, the y and z are going to be the same because we're going to define x direction as the only one that's changing. So this is actually really important for relativity. This is how we convert from one event to another. But we're going to take this a step further today and not stop here. And that step further is velocities. We learned in class that you can't have, you have a car and it's traveling half the speed of light and it turns on its headlights. How fast is the light when the headlights travel? And what was the answer? Speed of light. Doesn't matter what reference frame. Speed of light. And so our normal addition equation doesn't work. And so what we're going to do is we're going to say, well, how do we add velocities then? So we can calculate these velocities. Velocities are derivative. So definitions over here. U is going to be the speed of an object. So V is the speed of the reference frame. U is the speed of an object. Just using different nomenclature so we don't get ourselves too confused. So that's the difference in those. And so Ux is dx dt, right? That's the definition. Uy is dy dt. Uz is dz dt. Nothing shocking there. And of course, if you're in the prime frame, you just put primes on everything. Well, what we want to do is to relate Ux with Ux prime, Uy with Uy prime, and so on. So ux prime is dx prime over dt prime. Well, we have here what x prime is. So this is going to be d parenthesis gamma times x minus vt. Over, and time likewise, we have d parenthesis gamma t minus x v over c squared. What would we do from here? Oh, you in Calc 2. Chad gets off the hook yet again. What would you do? You what? Not L'Hopital's rule. That would be if we had a 0 over 0. But we have a d. It doesn't have with respect to anything, right? It's just a d. Well, what we choose to do is we say, okay, let's do top and bottom with respect to time. So I'm going to make this dt dt. Now, v is the speed of the reference frame. That's assumed to be a constant. We're doing special relativity, which has no acceleration, hence v can't change. And so if I do this, gamma is just a function of v, so gamma is not going to change. So there's my numerator. I'm changing colors willy-nilly. So there I've done the derivative with respect to time of the top and the derivative with respect to time of the bottom. Now let's simplify. What is dx dt? Okay, so that's and what is dt dt? 1, right. By definition, that's just 1. So I'm not going to write. I'm just going to end my parenthesis. On the bottom, dt dt is 1. And then we have v and dx dt. You told me was ux. Well, those gammas appear to cancel, don't they? And so we have ux prime is equal to ux minus v over 1 minus v ux over c squared. This is almost the same as what we would have for Galilean. I'm going to rewrite what ux and v are so that we can see that relationship. So we have ux is equal to the speed of my object. So I'm just going to use, well, I don't want to use O because it looks like original. So I'm going to put A for my object with respect to S frame, and V is the speed of, or S, that should have been S prime, speed of S prime with respect to S. So using Galilean transformations, we would have had V of A with respect to S. Oh, poo. If I have S prime, I have to have the prime on the U. It's the speed of object A in the S prime frame, and ux would be the speed of object A in the S frame. So speed of object A in the S frame is equal to speed of object A in the S prime frame plus the speed of the S prime frame with respect to the S frame. Remember our rule, these inside ones are the same, and then the first one is the first one, the last one is the last one. So that's what the Galilean transformation would have been. Putting it in terms of now these things, that is equivalent to u sub x is equal to u sub x prime plus v. Plus v. Oh, yeah, no, that's fine. It's correct. This here was ux prime. That's why I was like, uh-oh, I've got the opposite sign. So ux prime with the Galilean transformation, you would have had ux prime is equal to ux minus v. Well, here we have that same ux minus v on top. But we have a correction, if you will, for relativity down here on bottom. So you actually use the same formalism as you would use for Galilean transformation, just the normal addition of velocities, but then you have to divide by this factor of 1 minus v ux over c squared. So we derived, using these Lorentz transformations, how the speed of an object is going to be different in one reference frame compared to another, or how you add velocities. So let's take the example that I gave you at the beginning of this segment. Let's take the example where v is equal to 0.5 c and ux prime is equal to c, right? That's, you turn on the lights on your car that's traveling at 1/2 the speed of light. Then you would get, as you might have guessed, you can transform from one reference frame. Well, no, I actually found the ux prime instead of the ux. You can transform from one reference frame to the other by switching the sign of v. And so my speed in the other reference frame is going to be ux prime plus v over v times my ux. Oh, that should have been ux prime there, my mistake. So on the top I have 1.5 c, and on the bottom I have 1.5. The c's cancel actually.
Oh, yeah.
And that's equal to c. So this equation indeed says the speed of light is still going to be the speed of light. Now what if we did something that wasn't going the speed of light? Like, let's say the Falcon, the Millennial Falcon, is traveling. Okay, so I'm just going to put it in the bottom of this page. The Millennial Falcon has speed equals 0.8 c, and it fires its not a photon torpedo, because a photon torpedo would travel at c. We already did that. So it fires an actual physical torpedo at 0.3 c, a nice pedestrian speed. 0.3 c, we can't achieve anything like that, but hey, for Star Wars, or Star Trek, Star Wars, that's a pedestrian speed. So then we'd have the speed of that torpedo as measured from the unprimed frame would be 0.3c plus 0.8c over 1 plus 0.3c, 0.8c over c squared is 1.1c on top divided by 1.24 on bottom. And I'm sorry, I've got to do it. 1.1 divided by 1.24 and be 0.89c. So that's how velocities add in the x direction, which is parallel to the motion. I will finish this next week to calculate these here. All right, I'll see y'all in an hour and a half, except for Chad.